Hello, welcome to this week where we are going to start with modulation doping or high electron mobility transistors. This will again be in conventional 3-5 compound semiconductor family of starting with GaAs or gallium arsenide aluminum gallium arsenide system. But before we embark on the discussion on modulation doping and HEMT, there are just a couple of things that we had not touched upon in the last week's discussion on gallium arsenide MESFET, which is about what it takes to make a good low noise device out of gallium arsenide MESFET. So, maybe today the first few minutes we will just briefly touch upon some of these aspects of gallium arsenide MESFET low noise performance, and then we will quickly transition to the planned discussion on modulation doping. So, over to the whiteboard here. So, you see you can see here that what I am showing you here, and we talked about gallium arsenide transistor for power amplifiers and power application for sure, but gallium arsenide MESFETs have been also historically used for low noise amplifier. What I am showing you here is an equivalent circuit for a low noise a noise model or a low noise small equivalent small signal model. Okay. So, you can see here that within the dashed line this box is your intrinsic device, the actual device, and outside that are the extrinsic elements. So, for instance, this is your source resistance, this is your gate resistance, this represents the thermal noise originating from the source resistance, this represents the thermal noise originating from the gate resistance. Okay. This is a very important parameter IND. This is your drain noise, or it is basically the short circuit channel noise that is generated in the source drain path. Okay. And the expression for that, the noise power is given by this is 4 kT, temperature of course, delta F is the bandwidth over which you are measuring, Gm is the gain, and P is a factor. This factor P depends on the device geometry, bias condition, output conductance, etc., etc. However, this noise in the drain path, in the drain source path, which is basically the actual noise that dominates in most cases, the source of this noise is the current itself. The current itself generates this noise. Okay. And we usually operate this in say saturation regime. So, the mean square of the noise current, which is what I am mentioning here, this we also call it high field diffusion noise, because it is under high field saturation, it is under high field, and this is the diffusion noise that there is something called high field diffusion coefficient in gallium arsenide or any other material, and the noise originates from the carriers themselves because they are going in the channel, they are a significant source of noise, and this is the, you can say, the drain noise. Okay, the drain noise, that noise at the output you are talking. This noise here is the gate induced noise, or this is the noise induced at the gate terminal, and this is correlated to this in some way. Why? Because the origin is partially the same. What it means is that in a MESFET you have a depletion region. The depletion region, the width of the depletion can fluctuate because of the noise. When the current flows, when the drain current flows, you know, the ID flows, when the drain current flows, the width of the depletion can fluctuate by little amount. Okay, and that fluctuation in the depletion width, okay, that fluctuation in the depletion width can cause a fluctuation in the depletion charge, of course, because whenever the depletion width changes slightly, the depletion charge also will change, and depletion width is changing because of the noise voltage in the channel, which is basically this. Okay. So, your noise in the drain current, you know, there is a noise, there is an inherent noise, it basically makes the drain current fluctuate. That means the drain the depletion width fluctuates, which means the depletion charge also fluctuates, and if the depletion charge fluctuates, then the charge that it mirrors at the gate terminal also will fluctuate, because the gate is providing the charge, you know, the gate is mirroring the charge. So, any charge that is fluctuating in the depletion channel will also lead to an induced fluctuation of the charge in the gate metal. So, there is an induced gate charge, and these are correlated to the drain charge in a way. So, there is a correlated, and there is a correlation coefficient is J times C. It goes as I n g star, the complex conjugate of this quantity, okay, product of I and D, which is this quantity, and the product is, you know, you take the modulus of the product, or the, you know, the average of the product here, the value of the product here, and square root of ING square into IND square. Okay. This correlation coefficient, it basically kind of tells you to what extent these two noises are coefficient, and this is imaginary because the gate couples capacitively to the channel, and whenever there is a capacitive coupling, it is imaginary, of course. So, there is a capacitive coupling of the gate noise to with the drain, and so this is the correlation coefficient is imaginary, but this is just one part of the story, by the way. Do not think that your noise current will increase when your GM increases, it is not like that actually. You quantify the noise with a different figure of merit, it is called the noise figure. NF in microwave, in RF microwave. In your analog electronics we call it a noise factor, and we represent a noise factor, okay, noise factor, and the log of the noise factor with base of 10 into 10, this is called noise figure. Okay. So, noise factor, and so that is a more quantifiable metric. The noise figure or the noise factor gives you the actual overall feel for how the device is or the amplifier is in terms of your noise performance. Okay. Okay, this is your input, this is your output. At the input you have a certain signal, certain noise. So, there is a signal to noise ratio. Suppose you have a signal to noise ratio of suppose 100, signal to noise ratio of suppose 100. Now, you come to the other side, this will provide a gain G. So, whatever signal is amplified by G, whatever noise is here is also amplified by G, correct. However, this system will add its own noise also to that. So, overall the signal to noise ratio at the output here will be lower than the signal to noise ratio at the input, because the noise has increased. The signal is amplified, the noise is amplified, but the system is also adding an additional noise. So, the signal to noise ratio becomes worse or becomes lower at the output. This is signal to noise ratio at the input, okay, divided by signal to noise ratio at the output. So, signal to noise ratio at the input, if it was 100, then the signal to noise ratio at the output will be lower than 100, okay. It could be say 80, okay. So, essentially your noise figure will be 10 into log of 100 by 80, okay, that is your noise figure in dB. So, that noise figure, the best value of noise figure you can get is 1, the noise factor is 1, which means the noise figure can become 0, because your signal to noise ratio at the output can, the best case can be equal to that of input, okay. So, this ratio goes to 1, which means noise figure goes to 0. Okay, the noise figure of 0 is the best case scenario, which is theoretically the limit, and the idea is to, that is why, reduce the noise figure. The idea is to reduce the noise figure, which means you want to improve the signal to noise ratio at the output. Okay, signal to noise ratio at the input divided by signal to noise ratio at the output is your noise figure, the log of that is the noise figure. Okay, as I told you, the device itself adds some noise. That is why the noise at the output is more than what you would expect. That is why the signal to noise ratio at the output is lower, the denominator here is lower than the numerator. That is why the signal to noise ratio is, this ratio is always more than 1, and that is why the noise figure is always something like some dB. Okay. The idea is that this noise figure should be as low as possible. Now, the noise figure for a MESFET or for any other field effect transistor, people have done elaborate mathematics and analysis, and this is a simplistic expression. K is some constant, depends on the device, material, etc. Omega is the frequency, of course. So, at higher frequency of operation, your noise figure kind of increases, that is expected. Now, this is the minimum noise figure, which means whatever noise figure you get, there is a minimum noise figure you can get, which is not 0 by the way, is by matching the input and the output with optimal impedances. So, whenever you want to make a low noise amplifier, your input matching, especially the input side, has to be optimal for the minimum noise figure that you can get. You can get any noise figure depending on the impedance that you are presenting, okay, because it is all about impedance matching at the end. Okay. So, the device will have some impedance at the input, at the output, the load, the source, they will have their own load impedance, source impedance. The impedance matching has to be optimal so as to ensure you get the minimum noise figure, and that is called the F min. Otherwise, you can get any, and so F min is not necessarily what you desire maybe, because when you get F min, your gain will be also not so good. So, you have to trade off the minimum noise figure with gain also, that is a circuit problem. However, at a device point of level, here you see the minimum noise figure is plotted for a gallium arsenide MESFET technology at 4 gigahertz for a 2 micron gate, which is pretty long. The channel doping is 8 into 10 to the power 16 per centimeter cube. The source resistance is 15 ohm, the gate resistance is 1 ohm. Okay. And on the input side, you are plotting ID by IDSS. IDSS is the maximum drain current you can get, IDS is what you are biasing at. So, at 1 it means you are operating at the maximum drain current that you have. At 0.2 you are 20% of the maximum current. So, if the maximum current is 1 amp, you are biasing it at 0.2 amp of the drain current, you are allowing a drain current of 0.2 amp. So, you can see if your parasitic resistances gate and source were 0, this is the curve you would get, and in a reality when you have 15 ohm and 1 ohm, this is the curve you get. In both cases you can see that with higher drain current your noise figure increases, which is not a good thing. because higher drain current means, as I told you, the source of the noise is the drain current itself. So if your drain current increases, your noise figure also will increase, which is not a good thing. So you want to operate the low noise device at as low a drain current as possible, which is here at this point, which is around say 15%, 0.15 into maximum drain current. Whatever maximum drain current, suppose 1 amp is the maximum drain current, so you are biasing the device so as to get an output current of 0.15 amp only. In that case, you have the minimum noise figure. You are reducing it, the noise comes down because your drain current is coming down, correct. Here the noise increases because you are very close to pinch off, or pinch off as in not the drain pinch off I am talking about. I am talking about the channel pinching off and the device turning off. You are close to the threshold voltage. If you recall, close to threshold voltage, your GM is actually very low. Your GM is very low because if you recall, this is your ID, this is your VG, it rises like that, right. So near this point your GM is very low because the GM also follows a trend like that, right. This is your GM. So here the GM is very low near pinch off. So this part is near pinch off and your GM is very low, and because the GM is very low, your noise again starts increasing, the noise figure, because the noise figure depends extremely sensitively on the GM. Your GM should be really high to enable a good noise figure. If your GM becomes low because your input bias is low, I mean the current, because your gate bias, this is your gate bias is what you use to bias the device to decide on a particular current. So in that case, you decided that the current should be 0.15 amp on the drain. This is dictated by biasing the gate only. By biasing the gate, you decide ki, oh, I'll put at 0.15 amps of drain current. So you do not want to bias the device very close to the threshold or pinch off, because at that point your GM will drop down, and because of the GM dropping down, your noise figure will shoot up. So your drain current should be as low as possible as allowed by the lowest noise figure here. In general, for getting a low noise performance, typically your device is always operated at around 10 to 20% of the maximum drain current. That is the window you get to have the lowest noise figure here. In addition, you will see that because the source resistance comes between the source and the gate, correct. The source resistance comes between the source and the gate, and this source resistance is expressed as a unit of ohm millimeter, say 1 ohm millimeter or 2 ohm millimeter or something. So if you have a larger periphery device, if you divide it by a larger periphery, say 100 millimeter or 200 millimeter, I am just giving an example, the overall source resistance in absolute unit of ohm drops down, okay, absolutely, because your overall current increases. If your overall current increases in absolute amps, then your overall resistance in absolute ohms also drops down, okay. So with a higher W, your source resistance reduces, which means Rs varies as 1 by W. Rs varies as 1 by W, the source resistance drops as the W increases. However, the gate resistance exhibits the opposite trend. The gate resistance Rg actually increases as W. Why? Because if you look, if you recall the discussion we take, this is your gate metal, by the way, not Rs is about the in the channel, you have a gate here, you have a source here, this is a channel. So this resistance is in the channel, so that is why it is a channel resistance, that is why it drops as 1 by W. But gate metal is the gate metal, this is your W and this is your cross sectional area A. So the resistance is rho L by A, this L is actually W here, correct, L is W. So if it's rho W by the cross sectional area. So if your W, if your gate width becomes longer, your gate resistance also becomes longer. Think of it as a metallic bar whose length is increasing. In this case we call it width, it is a very confusing nomenclature, gate width not length, gate length is the other thing, but you can say this is the gate width in a proper in a terminology, you can say this is the overall bar, you have a metal bar and the length of the bar is increasing, which means the gate width increasing. So the gate resistance becomes as W. So this goes as W, this goes as 1 by W. So together they are kind of going in opposite direction. However, GM goes as W, the GM will go as W, which means if you have a higher W, your GM will become high. A higher GM is always desirable for low noise. However, the CGS outside, the gate source capacitance, this also goes as W. This is all inside the bracket of not bracket, under the square root, but this is outside the square root, okay. So this term will dominate over the other terms, as you can see this is outside the square root. So if in W increases, your capacitance also increases, right. Of course, your capacitance increases because if this is your gate, suppose this is your gate metal, this is your gate metal, this is your W, this is your cross sectional area, then the capacitance and this is your channel thickness. Suppose capacitance is epsilon naught epsilon s by this d, the channel thickness, into area. This area is, by the way, this area, which is your gate length into gate width. Okay. So, if you increase the gate width, your capacitance increases. If your capacitance increases, that means your noise figure also increases, which means gate width, with gate width the noise figure increases. That is the conclusion. The gate width increases with width, the gate resistance increases with width, the source resistance decreases with width, the GM increases with width, and the CGS most importantly increases with width. So, all this means that the minimum noise figure increases with increasing width, and which means if you have a larger W, your noise figure will be higher, which is undesirable. That is why for a low noise amplifier or low noise device, your unit gate width, say this is source, this is drain, this is your gate. So, this unit gate width should be as low as practicable, so as to keep the noise figure minimum. That is what it means. If there was no drain current effect, if there was no high field diffusion noise, then it will come like that, okay, only because of, but that is not what is reality. Okay. The reality is that it has this kind of a hockey stick behavior. So, you are on at this point, this is the near threshold, GM drops, okay, as a function of bias. This is with higher ID, the noise becomes higher. This is your sweet spot. With W gate width, the noise figure becomes higher with higher W. So, it is not desirable. So, you have to keep your gate width as low as possible. Gate length should be also shrunk down. Lower the gate length, lower is your noise, okay, and GM must be high, because a lower gate length will also enable you to achieve higher transconductance. Of course, I do not have to tell you that the gate resistance has to be as low as possible, because this is your gate resistance. You want to keep the gate resistance low, you want to also keep the source resistance low in general, so that your noise figure is come down. So, all parasitic components should be low, GM should be high, gate width also should be low, okay, and your drain current biasing should be such that the drain current is low as far as practicable. In that case, you are going to get a good noise figure. And this is the last slide from MESFET. This is basically two examples. This is fairly old, but the concept does not change. 0.25 micron technology. When they say 0.25 micron technology, it means the gate length is 0.25 micron or 250 nanometer. So, this is a 0.25 micron technology. You can see this gives you these are actually two low noise devices. This is on a epitaxially grown like MBE or MOCVD grown wafer. This is an ion implanted wafer where this channel is ion implanted. This is also ion implanted, this box is also ion implanted, N plus, this is epitaxially grown, this is N plus epitaxially grown, this is N plus epitaxially grown. You can see that this is your N plus region, and you have etched, this is the first recess and this is the second recess, correct. The first recess edge is around, you can see that this the second recess here is around 1 micron opening, and the first recess opening is around 3 micron, the gate is only 0.25 micron, correct. And you can see that the active channel is only 0.2 micron or 200 nanometer below the gate, but away from the gate it is around 500 nanometer in order to have high charge here. If you have high charge here, then your RS becomes low, here your RD becomes low with higher charge, but below the gate your channel resistance is higher than this and this, but that is okay, you have a better channel control. The thinner the channel, more is the resistance, correct. Same thing here, 0.2 micron of active channel, and then this is a 3 micron edge to edge of this, and this could be say 1 micron edge to edge, and the gate length is 0.25. So, in all these cases the channel doping was around 3 to 5 into 10 to the power 17. You cannot dope it too high, otherwise you will have start leaking, you will not have a good control on the channel. You cannot have too low, otherwise your channel current will be very low. You need a thin channel for better control, and if you get that, then you have higher GM, higher FT, and so you have a better noise figure, okay. So, with that the discussion on the gallium arsenide MESFET has been done, but we will now quickly move to the modulation doping, but this was the part of gallium arsenide MESFET for microwave noise application, which we missed out on the last lecture. So, I have just completed this in this lecture, but from now we will go to we will continue in this lecture only, we will go to the discussion on modulation doping or HAMT, okay. So, this is actually the lecture 21 that we are starting today. And how is gallium arsenide MESFET different from actually HAMT? Okay. So, for that we will have to understand what HAMT is actually. So, HAMT, okay, stands for high electron mobility transistor, high electron mobility transistor, because the electron mobility is very high. When I say high, it could be 10,000 for instance, okay, it could be 10,000 at room temperature, whereas silicon MOSFET the mobility is around 300 to 700. Gallium arsenide MOSFET may have little higher, but this is insanely high, 5,000 to 10,000 for instance, okay. So that is why it is called high electron mobility transistor or HEMT. Another name for HEMT is also called MOSFET in gallium arsenide system only, because you do something called modulation doping, okay, modulation doping. What happens is that when you have a material like a MOSFET which is n doped, okay, there all the electrons are here, free electrons which carry the current and which define the channel current ID, but all the impurities also there, the ionized donors plus 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 plus, right, all the ionized donors also exist there, they coexist with the free electron. So there is a huge amount of scattering. Do you know what is scattering? Whenever there is ionized donor like plus plus ions, then electrons get scattered from them, not physically by bombarding like two stones, but it basically like the ionized impurities set up a Coulombic field. There is a force field around the ionic impurities and they will scatter the electrons that are incoming. So because of this scattering we call it, this is an impurity scattering, and this impurity scattering can significantly lower the mobility, okay. So essentially what happens is that scattering gives you a time, you can call it the scattering time, or in more correct nomenclature you can call it momentum relaxation time. So essentially whenever an electron is coming and there is a positively charged ionized impurity, it will set up a force field around it, a Coulombic scattering will happen. So the the electron will be scattered, this is scattering, and this scattering will take some time, this edges consecutive scattering, we call it momentum relaxation time, the electron relaxes its momentum kind of, okay. So the mobility of electron is generally given by the charge times this momentum relaxation time divided by the effective mass. The effective mass being lower will always help. Gallium arsenide has a very low effective mass of 0.06 of the effective mass of electron and vacuum, of the mass of electron and vacuum. So this is constant for gallium arsenide across all gallium arsenide system, but it is much better than silicon or gallium nitride. So that is a different thing, but for a given material system this is constant, which means if you can actually increase the momentum relaxation time, your mobility will increase, and the momentum relaxation time can be increased, and this is by the way inversely proportional to the scattering rate, So the scattering rate reduces if your impurity scattering for instance can be reduced per unit time, how much scattering you are having. So if your doping, if your dope layer, whatever you are doping, this is your doping, but if this layer is not the current carrying layer, if your electrons are here, another layer, this is your layer of electron, this is your layer of doping. So the doping gives the electron, this is by the way not energy diagram, this is just a physical diagram. I am saying that in a stack, in a epitaxial stack, if the dope layer is here but that dope layer is not conducting electricity, the layer that is conducting electricity which is free electron is far away from this, then what it means is that the free electrons do not coexist with the dopant. In that case your impurity scattering will be minimal, okay. If you because the free electrons somehow are physically separated from the background doping, it means the area where free electrons are moving or carrying the electricity is away from the area where there is doping. If this is possible somehow, then the impurity scattering will become negligible because the impurity is far away, and if impurity scattering becomes lower, then your scattering rate will reduce, which means your momentum relaxation time will increase, and if your momentum relaxation time increases, your mobility will increase. This is the reason why high modulation doped transistor or high electron mobility transistor precisely does this by increasing the momentum relaxation time, by reducing the impurity scattering, by keeping the electrons away from the donor ions. However, phonon scattering will always be there, and that is unavoidable. Phonon scattering basically means that the atoms at any given temperature the atoms will vibrate like a spring, you can say. They can vibrate in phase, out of phase, transverse, longitudinal, etc. Phonon scattering is the atomic vibration of the atoms that will scatter the electron again with a potential that they will set up at any given temperature above 0 Kelvin. You will have phonon scattering. It will become much less pronounced as you go to low temperature. So, your low temperature mobility improves as opposed to high temperature mobility, but phonon scattering cannot be eliminated. It can only be mitigated by going to low temperature. So, phonon scattering will always be there. If you can remove impurity scattering, then significantly their mobility can be improved. This is the concept of modulation doping. And how do people physically do it? People physically do it by bringing a wider band gap aluminum gallium arsenide layer, an aluminum gallium arsenide layer with a gallium arsenide layer. This is about a slightly narrower band gap than aluminum gallium arsenide, correct. This is around 20% aluminum, maybe 80% gallium for instance. And what they do is that this entire aluminum gallium arsenide layer could be doped. It could be doped, and this is, when I say doped, that means n-type doped, so that positive ionized donors are there. This donor entire layer will be doped except for a few nanometer closer to the interface. This is your interface, no? This is your interface. So, except the interface, the entire thickness of the aluminum gallium arsenide is doped. Okay. So, these donors will donate electrons which will come and get trapped here. Okay. They will donate electrons, they will come and trap here. Because of this, they are donating, this will become depleted, and so the band diagram will look something like this. This is a conduction band, this is a valence band. Okay. This is a Fermi level at equilibrium, no light shining, no carrier flowing. Okay. And because electrons have come and accumulated here, this part will bend inwards. So, if this is your gallium arsenide, this will bend inwards like that. Okay. Okay. This will bend inwards. Okay. This is your EV, this is your EC. Okay. So, it has bent inwards. This part is n-type doped, say some 10 to the power 17 per centimeter cube, 2 into 10 to the power 17, 2 into 10 to the power 8, 3 into 10 to the power 17, something like that. And over here is your metal where you have the gate. I am drawing below the gate. This part, if I zoom in, it looks something like that, correct. So, this is your conduction band, okay, and suppose this is your Fermi level. So, at this part the Fermi level actually goes above the conduction band. What it means is that this is degenerate, which means it is an extremely high concentration of electron. It is a quantum well, by the way, a quantum well, a triangular quantum well. If you remember in your undergrad classes, we talk about quantum well, like in a potential in a well, like that, energy levels. This is precisely that, except that it is a triangle instead of a rectangle. So, this is a quantum well, there is a barrier here, there is a barrier here, it is confined there. So, it is a triangular quantum well. In a quantum well, like a triangular quantum well like that, you will have subband levels E1, E2, these are discrete eigenvalues, these are the energy levels that will exist, and the electrons are confined there. Alright. This has happened precisely because the electrons have been donated from the layer here to the notch here. They will energetically be favorable for them to come and form a accumulation layer there, okay, they have to form an accumulation layer there. Alright. And so, this is called modulation doping, because I am modulating the doping from another layer. I am using the doping here EC, correct. However, this is your, and the gallium arsenide inherently is mildly n-type, that is why the conduction band is closer to Fermi level. Similarly, aluminum gallium arsenide is also inherently mildly n-type, that is why its conduction band is closer to the Fermi level, but nevertheless this is not highly conducting. Okay, this is just mildly, it is unintentionally doped. That is why people use a chromium doped gallium arsenide to make it semi insulating, by the way, at the substrate level. Okay, the substrate, that is why the substrate is very low loss, low is very insulating substrate. So, this quantum well has different discrete levels, and electrons may occupy one level for instance, or maybe two levels. It is a quantum level, it is a quantum well, and if I say this is the z direction, this is the direction along which you are growing, this is aluminum gallium arsenide, this is gallium arsenide. So, this is the direction in which you are growing, which means if I look at the cross section, this is your gallium arsenide and this is your aluminum gallium arsenide. These electrons that exist, they exist as a sheet of charge. They exist as a sheet of charge which are confined in this quantum well. They cannot move in the z direction. This is because there is a well here. They can only move in the xy plane. which means there is a sheet of electron here, this is the sheet of electron which can move in this direction x, which can move in this direction y, which is the direction perpendicular to the screen of your computer or laptop or phone, okay, and this is your z direction. In z direction it cannot move because this is a barrier, okay, so it cannot move in the z direction, it can move in x direction, it can move in y direction. So if I take a wafer looking, this is from the side looking at the cross section, if I look from the top, this is a gallium arsenide wafer, you are growing aluminum gallium arsenide on top of gallium arsenide, then the 2d electron gas is everywhere here below, but it can only move in this x and y direction. If I put a top contact here and a bottom contact on the back side, can you measure current? You will not measure current because vertically the electrons cannot move. The wafer will break down, but it will not move, okay. But in the x and y direction you can move, which means you can make source here, drain here, or you can make source here, drain here, and they will move, okay, in both direction. So this is called a 2-dimensional electron gas. It is a gas, electron gas, we call it 2DEG, okay, it is called 2-dimensional electron gas. Alright, it is a 2-dimensional electron gas which is confined in the 2 dimension x and y, it cannot move in the z direction, and because of this confinement of electrons in 2 dimension, and this is, by the way, the doping is only here, it is away from the physical location of where the quantum well has formed, okay, it is away from the, so this part which is not doped a few nanometer is called a spacer. This spacer is precisely to separate out the dopants, the physical location of the dopant from the 2D electron gas. The spacer could be few nanometer, 2, 3, 4 nanometer, etc. That physically separates the doped layers, the doped layer from the point where the 2D electron gas has formed, so that your impurity scattering is eliminated or mitigated, okay. You cannot bring this spacer to too thin, maybe 1 nanometer you cannot make it, because if the dopant comes too thin, if the dopant comes very close to the 2D electron gas interface, then your impurity scattering will increase because of it is called remote ionized impurity scattering. Although the 2D electron gas, this 2D electron gas is not physically coexisting with the dopant, but if the dopants become too close, then they will start influencing remotely. That is why it is called a remote ionized impurity scattering. That is why a few nanometer of gap is kept, so that you have no ionized impurity scattering, they are physically separated from the 2D electron gas, phonon scattering exists, and that is why the mobility can be really high. And the fact that this is in a quantum well, it is in a quantum well, it is a 2D, the electron transport behavior and the scattering rate are also differently calculated for a 2D electron gas as opposed to like a bulk 3D, and so there is additional screening. When I say screening, it means there is a large density of carrier here. The density of this is always expressed per centimeter square because it is a areal density, areal as in area, over the area, areal density, it is an areal density over an area you are defining. So it is per centimeter square, and the density of this could be say 10 to the power 12 per centimeter square, which is a reasonably good 2D electron gas density. And at that such large electron density you have screening. What is screening? Screening basically means that if you have a large number of electrons around you, around an electron, then the scattering field of say impurity, remote impurity, etc. can be screened out, can be blocked to certain extent. So 2D electron gas has better screening because of high density of electrons in 2 dimension. It can screen out the ionized and other impurity or other scattering even more effectively, which is why the mobility increases even more. One is that of course your impurities are physically separate, that is one, but point number 2 is that a 2D electron gas is better at screening the scattering in general, it has a better screening capability. That is why your mobility becomes even higher, and that is why you get really high mobility, thousands and thousands, 5, 10, 10,000 at room temperature. At low temperature it can be really high, 50,000, etc. you can get in this material system, okay. The material has to be as pure as possible, of course, only in that case you can get it, okay. So this is the concept of a modulation doping, and this is the concept of a 2D electron gas that is formed, okay. Now what we can do is that we can next understand what is this density of electron that you are getting versus the different parameters that you have, the thickness of the L gas layer, the doping of the L gas layer, the metal Fermi level, etc., etc. As a function of those, how do you express the gate charge or the charge below the gate, because that is a crucial parameter to understand how the device works and to derive many device equation, okay. So with that we will end this lecture, lecture 21 of gallium arsenide L gas HEMT or modulation doping FET. In this lecture we just finished the discussion on the low noise part of MESFET and we started the modulation doping of HEMT. Going ahead in lecture 22 we will discuss in more details about modulation doping and derive the expression for threshold voltage, and also talk about the subband levels, the centroid of the 2d electron gas. We will also discuss about modulation efficiency, by the way. All these things we will discuss in lecture 22. 23, 24 will be more in the applied sense, we talk about the device as such instead of the physics of the device. Okay. So thank you for your time. I will meet you in the next lecture in lecture 22.